Hey guys, today I'm gonna start digital electronics, and in digital electronics I'm gonna cover this topics: Boolean algebra, logic gates, number systems, and sequential circuits. So in today's topic I'm gonna cover combinational gates and or not or. So let's go into them. So before going to the gates, I would love to say let us consider this is an digital system with an input and output. So the output will be generated based on the input and the functionality of this system. So the functionality of this digital system will be designed based on the Boolean expressions and the logic components. The logic components or the hardware are the logic gates, and this is which we are going to discuss today. So before going to logic gates, I want to say difference between analog signal and digital signal. Analog signal is continuous, whereas digital has only two values, either phi or 0 volts over here, whereas analog has various values from minus phi to phi. In digital, we have two logic levels, positive logic level and negative logic level. So as you can see from this, this signal has two levels, 0 volts and 5 volts. So 0 volts has a logic value of 0 and 5 volts has a logic value of 1. Whereas negative logic has the quite opposite of this. 0 volts has a logic value of 1 and voltage level 5 volts has logic value of 0. So in exams we might get either positive logic or negative logic. Be careful with the positive logic or the... So in exams, voltage levels or positive logic level or negative logic level must be seen clearly before answering the question. As you can see, this is the logic 1 and logic 0. This is a practical waveform, not the ideal one. So we have certain rise, not instantaneous rise. So above the threshold value it is logic 1, below the threshold value is logic 0, and the difference between the two threshold levels we get the noise margin. Now coming to combinational gates. And this is the AND gate, which is represented as shown. It can have two inputs or minimum of two inputs, A and B. It can have more than two inputs, and there should be only one output, C. So to get a better understanding of an AND gate, I'm going to show you a small network circuit. This is the source and this is the bulb. To turn on this bulb, we have two switches in between. So how can we turn on this bulb? So we need to turn on A and turn on B. Then only bulb will glow and the power will go from source to bulb. So this is the functionality of AND gate. Okay, this is a simple functionality of AND gate. If you remember this circuit, how the bulb is glowing, you can say the functionality of AND gate without looking. So this is the Boolean expression of an AND gate, and this is the truth table of AND gate. As you can see, A and B are the circuits and C is the bulb glowing. So when A is 0, B is 0, bulb will not glow. When A is 0, B is 1, bulb will not glow. When A is 1, B is 0, bulb will not glow. And when both are turned on, then only bulb will glow. So as you can see, it is quite relatable. So this is the Boolean expressions which are majorly used in any expressions for solving the problems. A dot 0 is 0, A dot 1 equals to A dot A equals to A dot A bar equals to 0. So you can compare with this truth table and substitute whatever value you want. You will get the expressions as shown. These expressions you need to have a brief look and you need to answer it very fastly for the competitive point. Next gate is OR gate. So the minimum number of inputs for this OR gate is minimum is 2. We can have more than 2, and this is the symbol of an OR gate logic diagram. So here it is represented in Boolean expressions, C equals to A plus B. To have a better understanding, let us look at this circuit. It will explain about OR gate clearly. As you can see from this, a source will give the power supply to the bulb when any of one of the switches A and B is turned on. So any of the switch is turned on will get the bulb as glowing. So based on this circuit diagram, we can have the truth table. So when A is 0, B is 0, that means both are off, then C will not glow. The bulb will not glow. When A is 0, B is 1, the bulb will glow because of B is turned on and the power will go through B. When A is turned on and B is turned off, the power will go through A and the bulb will be turned on. Similarly, when both are turned on, either way, no problem, the power will reach the bulb and it will be turned on. As you can see, any one of them is turned on, then we'll get the value 1. So this is the truth table of an OR gate. So from the truth table, these are the Boolean expressions which are mostly used in any expression to solve the problems. So 0 plus 0 is 0, 1 plus anything, as you can see 1 plus anything we are getting the value is 1. A plus 0 is A is 0 plus 1 equals to 1, 1 plus 0 equals to 1. If we consider A as 1, then we are getting the output value 1. If it is 0, it will get 0. And similarly, A plus A equals to A plus A bar A equals to 1. So you can solve this simple problem, substitute your values, you'll get the output as thoroughly. But do remember this because they are useful and easy to solve the expressions. The last basic gate is NOT gate. So this NOT gate has a simple functionality. That means whatever the voltage level you supply over here will get the opposite value. So to understand the NOT gate, this is a clear example of the NOT gate. As you know, when A is turned on, then the value at the bulb will be 0. It will be not glowing. When the bulb is glowing, then A will be turned off. Okay. So when A is turned off, we'll get the power over the bulb and it will turn on again. So this is the truth table of NOT gate. As you can see, when A is turned on, the bulb will not glow, so the output is 0. When A is turned off, the bulb will glow, the output is 1. So this is simple. It's represented by whole bar, 0 whole bar equals 1, 1 bar equals to 0, A double bar equals to A. This is the involutory property. So, and once again a brief discussion, C is equal to A dot B. This is an AND gate. C equals to A plus B. This is an OR gate, and these are its truth table, and this is the Boolean expressions which you need to remember because it's useful for solving the bigger Boolean expressions easily. So these are the 3 gates I have covered today. If you like this video, please subscribe because I need subscriptions, because I need them, because I need to have some audience so that I can feel good. Thanks for watching. Hope you like this video.